I'm just going to wait for the numbers to settle to get started. Okay, let's begin. On behalf of the National Woodworks team, I'd like to welcome everyone to our Wood Webinar Wednesday, featuring today's topic on exploring possibilities. Wood, it's not all straightforward. A few housekeeping items before we get started. There will be an opportunity at the end of the presentation for questions. To ask a question, please type your inquiry into the Q&A section of Zoom. We will be sending out certificates this week. The certificate can be used for self-reporting. Now, it's my pleasure to introduce today's presenters from RJC. Grant Newfield, Leon Plett, and Andrew Bayne are recognized leaders in the delivery of what is possible with wood. Together, they influence national codes, deliver first in what is possible in wood, and work collaboratively with forward-thinking architects and collaborators to turn creative vision into wooden possibilities.
Thanks, Keisha. Can I start now? Perfect. Good morning, everybody. So what we're gonna, well, I'd like to give a brief introduction to RJC. We're one of Canada's leading engineering firms. We're 100% employee owned. We have 14 offices across Canada, 74 years of providing service to Canada, and 587 staff nationally. Overview of what we're going to talk today about is curves and possibilities with woods, why, lessons learned, and best practices. We have 4 great projects we're going to introduce to you, and then we'll go into questions after. When we think of wood, we think of straight columns, beams, and flat floor panels, aligned in a regular grid. Sometimes we throw in the odd curve. However, if you really put your mind to it, wood can be very versatile in projects that are not so straightforward. The following examples will hopefully give you some insight into some pretty curvy buildings. The first project is the Great Northern Way Pavilion in Vancouver, BC. This project was envisioned by Chip Wilson, founder of Lululemon. He commissioned Perkins and Will, the architect, to come up with a unique design which would encourage dialogue and inspire creativity for the students and staff of the Emily Carr Institute and the PCI complex. As you can see, it really doesn't seem like a building you would create out of wood. Special thanks go to Ted Hall and the Spearhead team. They are the specialty fabricator and erector for this project who engaged RJC. And to Jeff Watts for the use of this presentation, which we presented in Banff in 2018, but they did a lot of the slides on it, and I couldn't have done better on it. So we'll start from here. So the first lesson we learned was the use of the integrated design process. The team included PCI, the developer, Perkins and Will, the architect, Ledcor, the contractor, Spearhead, the specialty fabricator, and RJC. We all worked together in a fully integrated design process. This allowed Spearhead, the wood specialist and fabricator, to be fully involved in both the design and construction process. This was critical to the success of this project. I'd like to briefly discuss the difference between a traditional design bid build versus an integrated design process. In the traditional process, the architect comes up with a vision, then working along with a team of engineers, produces a set of contract documents. These documents are then tendered to a contractor and their subcontractor without input. Often, there is little to no input by the constructors during the design process. In the integrated design process, the architect and engineers work along with the builder and specialty fabricator. The whole team is involved with the process well before construction starts. And in the end of the design process, the model created during that process becomes the digital link between the design and the fabrication. Before RJC was involved, the team looked at an LLT option. It had a high material volume and machining time, a high cost to construct, and an inefficient use of materials. When brought on, our scope was to provide alternative designs to the original proposed NLT structure, work along with Spearhead to develop the building form, and look for options to optimize the complex structure. We proposed two alternatives that were explored. The first alternative included glulam frames and a truss between the upper and lower petals. There was 10 petals in total, 5 on the outside and 5 on the inside. 3D modeling quickly indicated complex curvatures and double curvatures, complex geometry, difficult connections at the numerous nodes, difficult to construct, requiring shoring, and a high cost to construct and fabricate. The second alternative was to create an arched glulam dome as the main gravity system. Through the digital model, manipulation of the shape was used to simplify the structural form and create an efficient structure while representing the architectural intent. The arch structure included a compression and tension ring supported on 5 pedals designed to carry the gravity loads, wind, and earthquake. This form resulted in a very efficient and simplified structure. We used the model to review the design options and really understand the structure. In online meetings with Spearhead, we drew sketches for them to test each idea. Each idea was modeled to see if it fit the design intent or what types of clashings we would have. We also used the model to understand the wind and snow loading because it was a little difficult with the complex geometry. The primary structure was simplified into efficient forms. It included 5 inner structural wall petals, segmented for prefabrication, which included curved glulam members, secondary LSL framing, shown here as the ribs, a steel tension ring, and steel support mullions. The interesting thing about the LSL is when they actually form that's we'll call it timber strand, typically used for headers in residential applications. When they make LSL, they actually form it in a bed that's 8 feet wide by 60 feet long, either 1.75 inches thick or 3.5 inches thick. We were able to cut all the shapes out of that, just like taking a jig and plywood and cutting every unique piece to fit perfectly in place. The lower dome was formed to create an efficient arch structure, which included curved glulams as well, curved LSL secondary framing, twin members to suit the prefabrication of larger panels, and a steel tension ring at the base along with a compression lug at the top. The dome and walls were sheathed to provide shear wall and diaphragm requirements for lateral loads. We utilized 2 thin layers of plywood, glued and screwed, which allowed for the double curvature of the skin. The support structure for the upper pedals included short walls bearing over the glulam arches below, and an upper oculus acting as a skylight to support the 5 upper pedals. The upper pedals were formed of 3 primary sections: the lower pedal, the middle section, which rested on the dome, and the upper section, which rested on the oculus. There are approximately 7,000 individual CNC pieces, all fabricated through a digital model. The structure was digitally built from the ground up, breaking each architecturally unique form into shop fabricated assemblies that could efficiently be erected on site. The main difference between the integrated design process versus the design bid build was that the design happened during the process, not during construction. This allowed a single model to address all fabrication challenges. It also addressed interface details between dissimilar scopes, such as wood and steel or wood and concrete. Spearhead applied lessons learned from incorporating wood and steel on previous projects. Through their model, they supplied the cut files to the CNC plasma machines for cutting all the steel. This not only decreased the fabrication time, but also allows them to achieve far more stringent tolerance that is typical in the steel industry. The ring beam, once assembled, has a diameter of 18 meters, approximately 60 feet. The accuracy of a single digital model can be used to feed multiple CNC machines across numerous material scopes: steel, wood, concrete. This all allows for a tight fit up. And when brought together, the pieces should fit seamlessly. Through the integrated design process, the model for design becomes the model for the CNC machines, which cuts the pieces. The model also allowed the team to identify material parameters, optimize shipping, optimize the split up of members for prefabricating large pieces, ensuring optimal fit up under ideal conditions in order to reduce time on site. Spearhead and RJC in this case worked closely together, synergizing their ideas to create a form that best suited the project for design, fabrication, and construction. To address complexities, the pieces were fabricated and assembled in the shop to test fit adjacent pieces for each panel. This led to a no sawdust approach on site. The cut parts became the jig, which validates the layout. The sections were pre-connected in the shop to ensure fit up in the field. Shipping efficiency was also considered during the design. The accuracy of the digital model allowed us to eliminate challenges with complex geometry, test ideas, and vet the different options in a virtual build. As an example, the compression ring was developed through many go-to meetings where we sat in our office, Spearhead sat in their office, and we drew sketches virtually on the screen. We tested out various options. The design challenges included providing a connection that would allow moment transfer through the compression lug because there was uneven loading causing bending across this joint. Overcoming the complex geometry, the ring was actually in the curved section, ensuring fit up in the field. As well, the connection needed to allow the glue lam members, which were only 18 inches deep, to shrink over their depth. We could not have a solid steel section as it would not allow the beams to shrink. Through sketches, we developed a connection that would both allow the transfer of moment through the joint and allow the beams to shrink without restraining them. The shop drawings came entirely from the digital model. A test fit in the shop verified the model. The true test was during construction, when the connection becomes the central jig to connect all the arches. The central and outer ring was shored, allowing the wedge-shaped panels to easily be erected in place. A very tight fit was achieved in the field. When the shoring was dropped, we saw a 1/4 inch deflection over a 56-foot span. It's a span to depth ratio of about L over 2600. There were no RFIs on this install. In fact, there were no RFIs on the total project. The upper structure consisted of 5 pedals. The pedals were broken into 3 sections that were supported on short walls between the upper and lower pedals, and an upper oculus which acted as a skylight. Here you can see the short upper walls which rested on the lower dome, and the oculus, the vertical raised piece, in place. The walls were aligned with the glue lam members below. This provided supports for the 5 outer pedals. The outer pedals were differentiated into 3 sections based on their structural form. The 3 distinct sections shown here goes from vertical in the bottom, shown in blue, to horizontal, shown in red, to vertical, the last section that goes up to the top of the oculus. Some of the lower vertical sections were up to 27 feet long, to give you perspective. All assembled, the full pedals were about 60 feet in length. Each pedal was unique. Here you see the panels being fabricated in the shop. This is one of the lower pedals. You can see they're quite large. The pieces were assembled into the final configuration and match fitted against adjacent pieces. Then the pieces were shipped to site and erected in place. The benefits of the integrated design approach made possible the integration of all discipline requirements into the model, cross-coordination for all disciplines to a much higher level, and allowed for a much greater visual understanding through the design process. From the model, shop drawings can be produced fully coordinated with the model. If the model is correct, there's actually no need to check the shop drawings. From the shop drawings, the digital model is used to drive all the CNC cutting for both the wood and the steel. Accurate fabrication allowed all pieces to fit seamlessly. Panels were protected from moisture during construction to maintain their dimensional stability until the building was enclosed. There were no fit-up issues on site. It all came together very smoothly. The lower main structure was erected in about 2 weeks, and the upper structure, the upper pedals, in about 5 weeks, 7 weeks in total. 7,000 unique CNC cut wood components were shipped to site in approximately 90 assemblies, along with 5,000 small connectors and straps to connect the panels together on site. There were no typical details to interpret what needs to be done in the field, which is more common in a traditional build. No waste on site, no cutting or additional drilling, and no doubling up of orders, as quantities are all maintained within the model. And best of all, no RFIs and no shop drawing review, as this was complete during the design process. There's no doubt the integrated design process allows us to successfully complete projects with complex shapes in an efficient manner, far beyond what was done in the past. In understanding the limitations of each material, we're also able to create the unique shapes for each individual piece, which ultimately form this unique structure. I can only imagine a carpenter 40 years ago being given the task to construct this building. Takeaways. I would not want to take on a project of this nature as a design bid build. Using an integrated design process involving the fabricator's expertise made this project a success. Using digital technology and advanced processing for projects allowed us to streamline the structure and benefited a tight fit during construction. The model also assisted us in testing virtual fabrication, shipping, constructability, and finally understand the different types of materials available and how they can be assembled is key. Now we're going to move on to Leon Plett from our Victoria office, who's going to talk about the Craigflower Hall in Saanich. Leon?
Thanks, Grant. That was awesome. I hadn't seen your whole presentation before. It was really impressive, especially the work together with Spearhead and all of the detailed design. Really impressive. We're going to talk about a bit more simple project here in the small town of Victoria on Canada's west coast. This is Craigflower Hall in Saanich, which is home to the Victoria Highland Games Society. And the team members were D'Ambrosio Architecture and Urbanism, Frank and Erica, and especially Matt Jarvis, the lead designer on the project. Nappet Projects, who we worked with, they were involved start to finish in more of an informal IPD arrangement, and Struct.Eng, the timber supplier. You'll see some of their work here later as we go through. Next slide, please, Grant. The original vision for the project, are you flipping slides or am I not seeing it?
I'm on the next slide. It's showing a dining hall area.
Okay, it's not updated. Oh, there we go. So this is one of the original vision slides from the architect. Obviously, we wanted a circular space, open viewing to the waterfront. It's about 100 feet across, 32 meters or so across, open space through the dining area. Lots of glazing, obviously a feeling of timber and warmth, some reflection of the historic building on the same site. And the original idea was some glulam bent frames taking both moment and gravity loads, so seismic and gravity loads out through those columns, arranged at a central point. So next slide is some of our first feedback to the architect, where we, sometimes have to do some reality check to the original design. Thankfully, this was very early in the process. I'm still not seeing the updated slide. It's taken a little while. Thanks, Grant. And the concept was resulting in some very large member sizes, 1.2 meter deep glulam sections at the moment connection, a lot of seismic load being directed through that joint, and large connections required at the point. We were not able to arch this project as you were, Grant, on the pavilion, which would have really helped with those connection forces. but it really wasn't working well from an efficiency standpoint and from an appearance that the team wanted it to look like. So we regrouped, we worked very closely with Matt and the rest of the team at D'Ambrosio to come up with some options, and we'll flip through the pros and cons of some of those options here in the next 4 slides. The first option was just a pure, just a pure beam option to a central point with a moment connection there, but then a reduction of the connection through the moment connected columns and beams. Still resulted in a lot of connections and then some more seismic bracing to the steel columns themselves. Very simple suggestion. The second option, I should acknowledge as well, our project engineer was Cameron Marshall on this project. All of this great work was Cam, not me. So any credit goes to Cam. Any problems and funny questions should come to me. The other option we looked at was doubling up some glue lams and creating a more of a feature steel connection at the center. We need a lot of structural steel in there for the moment connection through the center of the span. So why not try to celebrate that a little bit? So that's what the second option was looking at. The third option was a reciprocating frame to create a bit of an oculus at the center and also reduce the member sizes and potentially simplify some of the connections. And the fourth option that we will not spend any time on at all was just a pure steel option, which was rejected forthwith. So where we landed with the design team and with feedback from the clients and the contractor was the choice of a reciprocating frame, actually a double reciprocating frame with a smaller frame in the center, which the clients really sort of appreciated as a bit of a reflection of Celtic Celtic knots, which we have some examples on the right-hand side. And so a bit of a celebration of the heritage of the building and the purpose. Architecturally very interesting, structurally quite efficient, and in terms of constructability, relatively straightforward as well. So we'll get into a little bit of the hows and whys and construction of this option. We're going to flip through some construction photos. Circular buildings have challenges due to our high seismic loads in Victoria and relatively poor soils on site. We went with a continuous footing around the perimeter. Pretty easy to build. We have we'll just flip through some construction photos here and we'll have some comments as we go through them. The lateral system was a combination of steel prong columns anchored to the concrete foundation, as well as some concrete and plywood shear walls. And due to the mix of systems, we were in a relatively conventional seismic system on the project. Moving along, we can see the glue lams in place and still wrapped for protection. You can see the scale of this roof spanning over 100 feet to the steel columns around the perimeter, fairly dramatic. We spent the structural budget on the reciprocating frames and kept the actual roof assembly above very, very simple. Just plywood on I-joists, keeping putting the money where it can be appreciated by the users and keeping the systems that can be simple, keeping them as simple as possible. It's just a picture from the underside. Another picture during construction as more of the joists are going in place. You can see the remainder of the building is relatively conventional wood frame construction, aside for some concrete walls that are feature walls and will be clad in stone. I really like this picture showing, the wide angle showing the underside of the reciprocating frame and the project as it's nearing completion. This project is in construction right now. It's not even clad in yet. It's glue lams were only lifted a couple months ago or so. It's moving relatively quickly, and I believe we've been posting some progress shots and drone videos from our Twitter account at RJC. So you can jump over there and see some videos, and I think Barbara might link some in the show notes here as well. Next slide, please, Grant. I think we're going to try to skip through this video that we had in here that was not working very well for us. One of the things I mentioned this as well before is the mix of simplicity and complexity, and keeping the things simple where they can be simple and cost effective. A very standard organization of joists and plywood forming the roof diaphragm, and then featuring the reciprocating frame where it can be appreciated from below. Sorry, I'm flipping through slides manually as we're following along on screen. Some of the lessons learned on the project were, it was nice to have 12 frames, and that worked out really nice from an appearance standpoint and that sort of thing, but it left an acute angle for the joist such that we had to use custom joist hangers for the eye joist between the beam members. And so perhaps taking a look at those angles earlier on, and this is where maybe a digital model would have helped us earlier on, is taking a look at those angles to see, could we get away with off-the-shelf joist hangers, for instance, in those cases early on. We also found that from an erection standpoint, it was really easy to put in 11 of these beams. The 12th beam, not so easy. So modifying those connections and making those connections work on site. This was certainly not a no sawdust site, and there might have been a little bit of field welding. All that said, it did go together really well with a really forward-thinking, problem-solving contractor. We've worked with NAPIT in the past on a number of fairly complex timber and steel and concrete projects with a mix of materials, sometimes with multi-curved glue lams. We did a project a few years ago with them where we had glue lam trusses with load-bearing glass king posts, and it worked out really well. So forward-thinking and creative project teams, I think that some of those benefits of a digital twin and all that money or all that time spent in pre-design, sometimes that's made up for with a creative and experienced team in construction. There's more than one way, I think, to achieve a successful project. And the trick is to know when is the right time to use those different methodologies. Next slide, Grant. So this is just reflective of a bit more of a linear design process than we saw earlier from Grant, where we started with early sketches and very, very simple models, force models, refinement of that through our work and refined design in coordination with the architect, relatively straightforward two-dimensional details, and then a really great set of shop drawings from Struct.Eng who came on board through the detailed design process and helped us refine those connections and the member sizing and the methodology and erection. It was really, there was great input from all of the team members on this project. I think we're on to the next slide. So just because we're on the theme of circles made out of straight lines, this is an art piece in Victoria, recently completed. Assistance from the project architect on the other project, Frank, designed by Bill Porteous, a local artist, and then construction by Kinsel Timber Systems at Esquimalt Town Square is an art piece. You can't really appreciate the scale of this piece from this picture, but it's relatively large and presents a portal and creates a circle out of squares, which I think is really cool. And now it's over to Andrew Bayne, who's the managing principal of the structural team in our Toronto office. Over to you, Andrew.
Thanks, Leon. We're going to talk about a couple jobs in the Toronto region. The first being the Toronto Regional Conservation Authority head office. Not quite as curvy as the last two projects, but just as complex in some instances. For those familiar with the region, oh, Grant, just hang on, I'll let you know.
Okay.
It's over at Jane and Finch, York University to the east, Black Creek Village, teams with Tennis Canada. We were teamed with Zaz Architecture and JV with Buchholz McAvoy Architects in Ireland. Element 5 was the fabricator, CM was Eastern, and erected by Timmerman. The Integral and MBI were M&E consultants on the job. It's 4-story mass timber, 90,000 square feet, no below grade. It's in the middle of a ravine, as you can see on the one slide. Perfect spot for TRCA headquarters. Lots of fun features, solar panels, solar chimneys up on the roof, full height, water walls, green roofs, skylights, the works. It's a little different. The procurement on this one was design, bid, build. Next slide. This is actually a little bit of history on the procurement, where it was provided as a visioning statement, as a master plan to us and the bid teams in 2016. A team of DTAW, Blackwell, Halsall, they all came up with a 6-story, 3-level underground mass timber job, 6x9 grid, very orthogonal. It was to be comprised of composite floors, utilizing 250 concrete, bubble deck, 200 CLT, and a raised floor. Next slide. I'm not sure if TRCA had mixed feelings, but through the next few years after our win with the team, we revisioned the entire project with the owner to their satisfaction. We did everything from cardboard models, old school, as shown on the screen. Next slide. Right through to our digital LOD 300 structural Revit model to work through options, VE, framing across the board. Ultimately, to support a competitive tendering process and a CM through public tendering, we gave a range of framing sizes. Next slide. So we ended up with a mass timber project still, only 4 floors. It was on a 6x6 grid, 6x7 grid, 6x10 grid. We ended up with 3 distinct wings, all slightly rotated to each other, not necessarily curved, but definitely offset. The ground wasn't that great in the middle of a ravine, so we did some ground improvements for conventional spread foundations to keep it economical with the help of Geosolve. We used raised floor, concrete topping. We ended up with just under 8-inch CLT, glulam beams, glulam columns. Everything was designed for a single tenant with 1-hour fire rating. CLT core walls combined with cross bracing, vertical cross bracing, horizontal cross bracing. And it did actually receive some NRCan mass timber grant funding at the time. So we did look at alternative approaches through this. At one point, it was an NLT system with plywood. We reached out to a number of different suppliers through the tendering process to also go through VE exercises. We had different approaches from Structure Fusion, Timmerman, Timber Systems. Ultimately, E5 was awarded the project in 2019, and 2020 we started working on shop drawings. Next slide. Current progress on site's about 95% erected. We still got some structural steel up on the roof and little miscellaneous elements to go, but it's for the most part in place. The one slide shows the atrium space on the left in between 2 of the wings. In that atrium space, there's a water wall at the end that has yet to be framed near some of the bracing, the skylights over top of the entire system. It really speaks to the sustainability for LEED Platinum, WELL certification, net zero, a lot of the sustainability approaches that were taken on the job. And then on the right side, we've got some exterior views showing some of the same bracing systems that are currently present. Next slide. So with all these wings slightly rotated and orthogonal, we did wind up with some tough complications on framing. Mass timber loves to be repetitive, typical bays, and in some of these locations where the grids intersected, we were anything but. But we worked with the team real close to make sure we could keep it as simple as possible. It was all exposed, so nobody wanted to see any clunky, heavy connections. So on the screen is one of the 3rd floor roofs over one of the skylight atrium spaces between wings. And a little snapshot of some of the grids highlighted where all the different beam layouts were intersecting. So there was a lot of different studies on trying to make that as simple as possible. So with those 3 orthogonal wings and those skylights, all those overlaps, we worked with the team, standardized as best we could, and create those clean lines. In the end, it's still aesthetically pleasing, and the owner was still very happy with the way it's laid out. But at a glance, it does come across sometimes as not quite lining up, probably on purpose. Next slide. Some of the interior spaces were fairly complex, trying to, again, to work with the architectural team to make them look simple. We had the perimeter of the building utilized a number of vertical and horizontal bracing to provide stability, where some of these conditions, like on the screen here, were combined at clear 2-story high atrium spaces with gathering spaces overlooking the actual exterior, seeing all the trees in the background, the ravine, perfectly combined with TRCA's mandates. The screen shows some of our original design intent drawings, clarifying geometries, working points, design intent, progression through some of the shop drawing connections of the same, where you get right into screw locations, bolt locations, plates, bent, notches, everything that was going to be cut out on site or in the shop, and ultimately the as-built condition in the picture. Next slide. What am I doing on time? Okay. The other project is Centennial College, A block at the 401 Markham Road. It's a new build with renovation and tie into the existing A block building. We were teamed with Ellis Dawn on this pursuit with Dialogue, Smoke Architects, Nordic Structures. Smith and Anderson were on the M&E side, RDH on building science, Vortex, fire. It was 5-story mass timber, 150,000 square feet. Again, a lot of sustainability with LEED and well, I think it was 0 carbon, with also a very strong Indigenous focus on this one. Next slide. Procurement on this one was design build. We were provided an RFP and a qualification back in 2019 to team up and work through it, but we were only provided a owner's requirement spec, no drawings, so we dove right into modeling immediately and trying to work through our own bid and presentation. And thankfully, after a year or so, 2020, we were the successful team, the procurement team. Next slide. On this project, Nordic was engaged at the end of schematic design and was a very important player and worked collaboratively with the design team to economize on the materials that they could procure, their manufacturing techniques, their sizes, preferred connection details, and the works. We worked very closely with them regularly to make sure, as engineer record, that we were all on the same page. We ended up with a 10 by 6 meter grid, again, with some concrete topping and 175 mil CLT floor panels for 1 hour rating. Some areas required a 2 hour rating, and we ended up with slightly thicker panels and slightly thicker concrete topping. Glulam beams, glulam columns throughout. Large glulam beams as a result of a lot of the strict performance criteria and targets that were set by the college. Primarily vibration. So on those longer spans, when vibration starts to govern, the beam sizes do exponentially get larger. We also utilize concrete cores around the elevators and stairs and some wood bracing. Next slide. The architectural cladding was also a strong expression. It did require some structural steel framing to complement the mass timber. And to support a lot of these unique conditions. I think there's a handful of architectural stories for just about every little corner of this building, which I won't speak to because I will butcher it, but it still highlighted a lot of the exposed mass timber wherever possible. Next slide. Current progress on site. This is a picture from the fall. Pre-snow anyway, where you start to see the building up 3 floors. Some of the jointing connections become more obvious now, where we relied on a lot of bearing conditions, beam to column connections with as little steel as possible. You can start to see at the bottom of the screen some of the feature stairs starting to take shape, also built up out of CLT panels. And on the far right, some of the cross bracing starting to grow up out of the ground. Next slide. And this one's one of the more recent pictures. They've, again, they're now about 95% done, placement of all the mass timber. They're working on the cladding. Tower crane is still up. Next slide. Lots of cool features on this project. Picked a few to just highlight today on our presentation. The first one highlighting really the importance of multidisciplinary coordination. So this slide shows the transition from the top left through some of the pictures on concepts to help integrate mechanical electrical services with mass timber. A lot of big beams, trying to not punch them full of holes since it's all exposed. The 10-meter spans and a lot of those tight vibration serviceability performance criteria made running ducts between classrooms complicated. So we ended up taking our 10x6 grid and shoving it a little closer together and following the corridor with our one line of columns. And what that did was enable a shallower beam system over the corridor, and then actually relying on CLT's inherent two-way capacity for a little bit of span without any beam support, which let us squeeze the floor-to-floor heights in the building while maintaining some economics through the M&E design and keeping the ceilings in the classrooms nice and high and exposed. Few minor openings through the beams for future flexibility, sprinkler lines, some electrical IT conduit, but very minimal, with most of it being run in the corridors. Next slide. Again, trying to just create simplicity out of the complex. So on this, we have another nice image of a braced bay, a vertical braced bay frame, all mass timber. Highlights in some of our earlier sketches, the geometries, the design intent of the original drawings through shop drawing process and the coordination that took place there, and making that connection on site as the as-built condition look fairly straightforward and simple, although it never is. So you can see some of the nice knife plates, screw holes ready to come to accept the floor above. There's hidden beam connectors in and out of the page or in and out of the element here for beams framing for the floors. And hard to see, but dozens and dozens of screws per connector, but comes across very aesthetically pleasing. Next slide. It was discussed on some of the earlier slides and presentations about some of the CNC and the digital fabrication. Nordic ended up designing a lot of bearing conditions, and to do so needed a lot of tight milled end joints for their columns and their beams. There's a nice picture on the screen that just shows how this came together so simple on site when everything was trucked in from Quebec and placed, and it went up fairly quick. Everything just required a few bolts and a few screws to hold together, relying on very tight, snug fit bearing connections. Not a lot more to say there. It's just a cool shot showing some of the geometries before everything's covered up with floor plan panels. Next slide. I want to finish with an interesting space in this project. It's it's a curved wood enclosure interior space in the focal point of the building for the Indigenous common gathering space / smoke room. The code consultants had their hands full with an open fire and smoke in the room, but all is well, and it's still moving ahead as planned. The slide shows a secondary structural frame within the building through isometric designs and shop drawings with the render, with a main focal point through a 2-story high space with a curved circular glulam out of plane. It's just under a 5-meter diameter, and it's been curved. On the next slide, you will see the current as-built condition of that same curved element. Figured we had to finish with something curved in place with the blockouts ready to go and some of the nice bracing in the background. So I want to leave it there for today and pass it over to Kesha again.
All right, that was wonderful. I really enjoyed all of your presentations there. We do have a few questions. Let me just pull them up here. Okay, so any one of you can feel free to answer these questions. The first one we have here is, why did you choose to make the pavilion out of wood?
Okay, Kesha, I'll take that question on. There was a strong desire from the team, including Perkins and Will and the developer, to come up with something that was sustainable. When we first looked at it, we thought, oh, it's going to be difficult to actually make everything curved like that and do it out of wood. But we really, we have a strong understanding of materials and what works in different places. If you're to do that in concrete, well, I wouldn't want to go there. Structural steel is certainly an application for it, but the heavy curving of members and the complex geometry is very difficult to work with steel in that. It actually turns out that wood is actually probably the material that I would do that out of, very much like building a boat. There's ribs, there's curved members, we have glue lamps to curve, we have a timber strand, which we can cut all the ribs out of, all the different shapes. And we can coordinate that with structural steel. And in the end, well, when I started, I thought it was going to be maybe another material, but in the end, it really made sense to do it out of wood. And I thought that was actually the right material for it. We have the plywood, the LSL, and the curved glue lamps, which all have abilities to curve.
Great, thank you. Next question. What was the total project cost, construction, and consultant fees for this pavilion?
Well, I can't give you the fees over. I'm not going to go into the fees. We got actually hired by Spearhead, the specialty fabricator. So our fees were through Spearhead as part of their package. The whole pavilion with the zinc, I can't give you the total cost on it. I know the structure in place was over $1 million, but there's a lot of work in fabrication to put that together and logistics. So the full fit out is north of that figure. I'm just giving the structural portion.
Okay. What was the software used for the GNW Pavilion?
The software? Well, Spearhead did all the modeling. I think, I'm not 100% sure. I think they work in CADWorks. We actually have our own design software at the office, SAP and ETABS that we use for looking at things like this. But they were doing the digital modeling, which creates the digital files for the CNC machines. And that was all done through, I'd have to double check on that. I think it was CADWorks, but it's a process for doing that. We actually didn't even meet with them in their office. We just sketched up on the computer screen on tablets, and they took our sketches and they would come back a day later. They would model everything and they would come back a day later telling us what worked, what didn't. Very, very powerful group for modeling and creating complex shapes. It was actually an easy process for us, and it was a lot easier for us to understand the structure because of the modeling.
Great, thank you. Next one is, what are the best practices on protecting mass timber from the environment during construction?
Well, if you look at the job with snow, it's definitely trying to keep the moisture down when that all melts. So they're constantly maintaining, covering. Some critical elements are protected on site with corner bead, wrapped in saran. They're trying to protect not only during construction, but from the elements. We've seen a number of different approaches to the ongoing maintenance and water mitigation through construction. Very critical. Don't want to trap too much moisture before you get that building enclosed. On to you, Leon.
Well, you answered a lot of the points there, Andrew. I think, moisture protection is very, very important in any sort of timber construction, whether it's stick frame or mass timber. It's a very important part of how it goes together. Benefits of mass timber is often speed, in that columns and floors can go together quickly and are not as exposed to the weather for as long. As you saw in a number of the pictures that we were showing, is protection is often supplied from the shop all the way to site and only removed once it's about to get covered. Careful to make sure that those coverings can breathe. We've seen problems in the past with overzealous protection of timber and not allowing it to breathe. Wood is meant to breathe and change moisture content over the seasons and over time. So wood is very resilient and able to protect itself during that process. but we have to do what we can to make sure we avoid any staining or any permanent damage to the timber during construction. I saw one of the questions about concrete topping as well, perhaps counterintuitively, as the concrete cures and normally topping mixes are relatively wet, making sure that the concrete topping itself doesn't present any moisture to the material, and whether that's protection of the timber through some sort of a membrane between the concrete and the timber, or paying other attention to mitigating that damage is important as well.
Great. That's it for our questions. Would one of you like to add any more feedback, or we can wrap it up for the day?
I don't have any more feedback. Do you guys have any more feedback?
I think we did a good job.
Yeah. That was fantastic. No, well, thanks for the opportunity, and it's great to see the CWC putting these presentations together, and hopefully some of the anecdotal stories and things people can take away and look at things a different way. Wood is a very versatile material. Just really understanding it, how it works, all the different types of materials that you have in timber or mass timber. If you understand those strongly, you can do a lot with wood. So,
yeah, that's great. Thank you so much for your wonderful presentation. It was fantastic, and I thoroughly enjoyed it, and I'm sure everyone else did as well. Thank you, everyone, for taking the time out of your schedule for joining us today. You can win a $70 Amazon gift card by filling out a short survey that will be sent out in 2 weeks to gauge your webinar experience from today. We appreciate your feedback and look forward to your comments. Thank you, and have a great rest of your day.
okay, thank you.
Thanks.